At 03:14 UTC on November 6, 2025, a partial data stream from NASA's Deep Space Network arrived at the Jet Propulsion Laboratory. It wasn't supposed to. The telemetry was flagged as incomplete, the packet headers mismatched, and the signal strength suggested that the origin was more than 2 AU from where it should have been. But one detail made the engineers stop talking. The source ID belonged to 3I Atlas. The interstellar object had already passed perihelion on October 29th. Its outbound trajectory was predictable, stable, quiet. Every simulation, NASA's, ESA's, even the independent ones from the Minor Planet Center, showed a simple fading arc away from the sun. No more surprises, no more sudden brightening, no more unexplained activity. So why did Hubble and JWST both record a spike, an intense, narrow-band flash from the object's coordinates? The flash lasted 0.14 seconds. Too short for normal comet outgassing, too bright for a dust ejection, too sharp to be an artifact. JWST's NIR spec registered a surge in the 3.1 to 3.3 mm range, something between reflected sunlight and thermal radiation. Hubble caught a faint streak on the UVIS instrument, a structured line, almost like a filament twisting in the solar wind, and then came the second anomaly. The reconstructed motion vectors from the James Webb images suggested an acceleration of 0.87 ms2 across a window of 20 minutes. That may sound small, but for an object nearly 700 meters across, now losing mass at a rate of less than 0.2 tons per hour, that acceleration made no sense. A comet can't suddenly push itself sideways unless something dramatic happens inside its nucleus, except there was no outburst, no thermal effects, no obvious jet. Just a quiet, steady shift, as if the object was adjusting its path. Is that possible? Yes. Is it expected? Absolutely not. Scientists dug deeper into the incomplete feed. 3 frames from Hubble's WFC3 instrument appeared corrupted. But when the corrupted segments were enhanced, something strange emerged. A faint, geometric shadow inside the coma. Triangular edges, a pattern too straight to be dust, too consistent to be random. Most of the team dismissed it as compression noise, but 2 researchers, Dr. Helena Rhodes from NASA Goddard and Dr. Marco Ishida from ESA's Gaia program, noticed something else. The geometric shape aligned with the direction of the unexpected acceleration. Coincidence? Artifact, or something structural inside the nucleus shifting under solar stress. The scientific community has seen comets fracture, shear, spin, and even split, but never reorganize, never exhibit coordinated internal motion, never produce a signature that mimicked energy being stored and released. To make things more complicated, NASA's public dashboards went dark for nearly 4 hours during the anomaly. A software glitch, they said. Routine maintenance. But the timing couldn't have been worse. For the first time since perihelion, the data raised more questions than answers. Why now? Why this object? Why a signal spike at a wavelength no comet should produce? And most importantly, what exactly did 3I Atlas do out there in the dark? The first official meeting about the anomaly took place on November 7, 2025, inside Building 34 at NASA Goddard. The agenda was supposed to cover routine post-perihelion tracking. Instead, the room filled with quiet tension as Dr. Helena Rhodes projected the latest orbital reconstruction of 3I Atlas onto the wall. Something was wrong. The object's outbound path, calculated independently by NASA, ESA, and JPL, showed a deviation of 0.003 AU from the expected arc. Tiny on an astronomical scale, but impossible to generate without a force significantly stronger than standard outgassing. You don't move a 700-meter interstellar body sideways unless something acts on it. Is this an observational error? Someone asked. It wasn't. 3 telescopes confirmed it. Pan-STARRS, TESS, and JWST. 3 different instruments, 3 different wavelengths, same result. The room went silent. Then came the second dataset, the incomplete feed from the Deep Space Network. Engineers had stitched it together, frame by frame, until a 1.7-second sequence emerged, grainy, unstable, but unmistakably real. A ripple passed across the coma, like a pressure wave moving through dust. But the wave wasn't spherical. It traveled along a straight axis, then branched at a precise 27-degree angle before fading. Natural comets don't do that. The ripple, aligned perfectly with the geometric shadow detected earlier in Hubble's corrupted frames. A pattern inside the nucleus, a fracture plane, or something reorganizing under the sun's radiation. Dr. Rhodes paused the footage. She zoomed in. A cluster of pixels lit up in a sharp, blade-like shape. "If this is dust," she said, "it's the most symmetrical dust I've ever seen." No one laughed. To understand the event, the team compared the ripple to past cometary behavior. They reviewed data from 67P Churyumov, Gerasimenko, Borisov, Halley, and even Oumuamua. But none of them showed a directional shockwave without mass loss. Comets shed material when stressed. They break, they spray, they melt, they don't pulse. And yet, something about the brightness spike suggested a controlled release of energy, short, precise, targeted. The wavelength, 3.13 nanometers, didn't match typical ice sublimation. The thermal signature didn't match a natural outburst, and the acceleration was too smooth to be chaotic. Was this a structural collapse inside the nucleus, a deep crack aligning with sunlight, a trapped pocket of volatiles venting sideways? Every hypothesis had the same flaw. None explained the timing. Why did the anomaly occur exactly when 3I Atlas passed beyond 1.1 AU, entering a region where its activity should have been dropping, not increasing? Then another detail emerged. JWST's MIRI instrument detected a faint radio sideband modulation, not a signal, but a distortion pattern, synchronized with the moment of acceleration, like the object briefly interacted with the solar wind in a way no natural body ever recorded. Attention filled the room again. Someone finally asked the question, "Are we watching it break apart or turn on?" It was rhetorical. No one dared guess. The team prepared a formal bulletin for NASA headquarters, labeling the event non-standard post-perihelion dynamics. They avoided stronger language. No speculation, no conclusions, but the private notes circulated among senior scientists used a phrase not seen since the early Oumuamua debates, unknown internal mechanism. Meanwhile, the public NASA dashboard came back online, with the anomaly omitted, not hidden, just missing, as if the system had rolled back to older data, a software sync error, a timing mismatch, or something else. For now, the object continued drifting outward, silent, dim, and, if the acceleration graph was accurate, no longer entirely passive. Something happened inside 3I Atlas. Something that changed its behavior, something that the data could describe but not yet explain. At 22:08 UTC on November 9, 2025, a new set of frames arrived from the Transiting Exoplanet Survey Satellite, TSS. TESS usually scans for dips in starlight, not for interstellar debris, but the anomaly prompted NASA to widen its monitoring net. Engineers pointed one of its sectors toward the predicted outbound path of 3I Atlas, expecting only a faint thermal blur. They got something else. Frame 119 showed a silhouette, barely visible, only 5 pixels long, but with edges too clean for dust and too rigid for a fragment. The object moved with 3I Atlas, its position fixed relative to the nucleus. If it were debris, it would drift. If it were noise, it wouldn't persist across 3 separate exposures. Dr. Marco Ishida stared at the overlay in silence. "It's holding formation," he finally said. "Formation. Comets don't have formations." NASA ran the data through noise analysis. They checked for cosmic rays, tracking errors, sensor reflections. All negative. The shape was real. Not large, maybe 14, 60 meters across, but its geometry implied something with mass and structure, not a cloud of particles. The team overlaid the shadow with the geometry from Hubble's corrupted frames. The angles matched within 4%, too close to ignore, too strange to accept. Rhodes looked at the composite. Is it a cavity inside the nucleus? Maybe, Ishida replied. But why is it visible outside the coma? The next dataset complicated everything. The Solar and Heliospheric Observatory, SOHO, captured a faint ion trail trailing 3I Atlas, thin, focused, and remarkably constant. Unlike typical comet tails, it didn't bend much with the solar wind. It stayed aligned with the object's new trajectory, almost like a guidance line. The ion ratio showed elevated Ni-Fe, similar to earlier Atlas readings but now more concentrated, as if the material was being released through a narrow channel rather than a broad outgassing surface. Natural jets scatter. This one pointed. Meanwhile, the acceleration continued. Subtle, consistent, measured at 0.54 mm S2 over a 48-hour window, small enough to miss in a casual scan, large enough to redefine models of interstellar comet behavior. NASA convened a second emergency review, this time with specialists from ESA, JAXA, and the Harvard-Smithsonian Center for Astrophysics. The agenda: identify mechanisms capable of producing coordinated motion in a mostly inert, icy body. 3 proposals emerged. 1. Internal crystallization, sunny-side heat reaching preserved volatiles, triggering controlled sublimation along fracture lines. Elegant, predictable, but it couldn't explain the geometric shadow or the stable ion trail. 2. Magnetic interaction. Some interstellar dust grains have magnetic properties. Could solar wind compression be forcing aligned movement? But the observed effect was too directional, too coherent. 3. Fragment coupling. A piece of the nucleus breaking off but remaining gravitationally locked in a rotating configuration. Possible, but the shadow moved without rotation, contradicting the idea. All explanations failed on at least one measurable point. Then came the strangest data of the night. JWST's NIRCam, using a long-exposure deep-field mode, captured a microflare, a one-frame burst, almost like a spark, originating from the dark side of 3I Atlas. Not sunlight, not thermal emission. The wavelength matched the earlier 3.2 mm spike. Dr. Rhodes leaned forward. That's the same signature, she whispered. The same event repeating. But this time, the spike was followed by a small, precise motion, a course correction of 0.007 AU, barely measurable, yet undeniably real. 3I Atlas wasn't drifting, it wasn't tumbling, it wasn't breaking apart, it was adjusting. Scientists looked at the data and saw something they didn't dare say aloud. A pattern, not intelligent, not artificial, just consistent enough to be unsettling. The meeting ended past midnight. Nobody raised their voice, nobody speculated. But the tension said everything. Nature can surprise you, but nature rarely does so with straight lines. On November 12, 2025, at 0441 UTC, a message appeared in NASA's internal alert system, short, technical, strangely calm for what it contained. Atlas outbound luminosity rising, no thermal correlation. Review priority high. Outbound luminosity rising. That alone was enough to hold 3 ongoing briefings across Goddard. Comets brighten near the sun. They fade when they leave it. It's one of the simplest laws in comet science. Sublimation drops. Dust output decreases. Photons scatter less effectively. And yet, 3I Atlas, now past 1.3 AU, was getting brighter. The anomaly was subtle, only a 0.07 magnitude increase over 8 hours, but real. Verified by 3 instruments, Pan-STARRS, Gaia, and the Vera Rubin Observatory. All detected a glow that wasn't thermal, wasn't dust, and didn't match any model of solar illumination at that distance. The first suspicion was instrument contamination. It wasn't. Second suspicion, a tail alignment illusion. Also ruled out, so the team looked at frequency bands. That's when they found it. The brightness spike occurred in a spectrally narrow band centered at 890 nanometer, a wavelength associated with coherent reflection rather than diffuse scattering. In simple terms, not a natural glow, but something closer to a surface brightening in a specific, controlled way. Controlled by what? Dr. Marco Ishida pulled up JWST's latest deep field mosaics. He isolated 143 frames, filtered noise, removed cosmic rays, and compiled an RGB composite of the outbound coma. What emerged made the room lean forward. Inside the dust halo, faint but unmistakable, was a biped, rotating alignment of particulate arcs. 3 curved filaments turning in slow synchronization, like petals drifting in a current. But their spacing was too perfect, their motion too smooth, their curvature too consistent for random debris. And all 3 arcs turned toward the same direction every 23 minutes. Dr. Rhodes froze the frame. "Is that precession?" she asked quietly. "A natural nucleus can precess as it spins." But 3I Atlas wasn't spinning fast enough. Its measured rotation period was nearly 173 hours, glacially slow. But the arcs inside the coma precessed every 23 minutes, almost 8 times faster than the nucleus itself. 2 rotational regimes, 1 body, no known mechanism. Even stranger, the precession always pointed toward the object's new, slightly shifted vector, the same direction of the ion trail and the course adjustments. Rhodes ran a simulation. If the arcs weren't particles, but shadows cast through a semi-transparent medium, perhaps from interior density gradients, they could theoretically rotate independently of the nucleus, but that still didn't explain the precision, or the rising luminosity, or the alignment. Then came the data that changed the tone of the entire investigation. The European Space Agency forwarded a packet from their solar orbiter probe. It recorded a weak, rhythmic fluctuation in the solar wind, barely detectable, coinciding exactly with the precession period. A pulse. Every 23 minutes, low amplitude, consistent, radiating outward like a soft, periodic handshake between the object and the environment. Solar wind doesn't pulse like that. Comets don't generate pulses like that. Ishida stepped back from the screen. "It's not sending anything," he said, "at least not intentionally." He emphasized the last word quickly, as if regretting it. "It's just interacting with the solar wind in a way we've never seen." That was the most conservative interpretation anyone could produce. In the briefing notes that followed, NASA used the phrase harmonic solar wind coupling, a cautious technical descriptor for something no one had a name for. Outside the walls of the conference room, Atlas drifted silently into deeper space, glowing stronger than before, shedding structured shadows, adjusting its course with microbursts no one fully understood. The object was no longer just unusual, it was consistent, predictable in its unpredictability, and that was more unsettling than any one anomaly by itself. By November 14, 2025, the scientific community reached an uncomfortable consensus. 3I Atlas was no longer behaving like a single, cohesive object. But it wasn't breaking apart either. This contradiction came from a new data set delivered by the Very Large Telescope, VLT, in Chile. Using adaptive optics at extreme resolution, VLT observed faint discontinuities in the coma, thin, dark seams where dust density dipped sharply, almost as if the halo were being divided into segments. Comets sometimes show fragmentation patterns, but fragments drift outward. These seams didn't. They moved with the object, maintained spacing, maintained orientation. It looked less like a body crumbling and more like a body reconfiguring. Dr. Helena Rhodes enlarged the frames. The seams formed 3 concentric layers, rings of reduced particle density. At first glance they resembled shock fronts, but the velocities were all wrong. Shock fronts propagate quickly. These moved slowly, precisely, like tectonic plates sliding under extreme pressure. Under the sun's influence, under internal stress, under something else? To cross-check, NASA turned to something unexpected. Radio occultation. When 3I Atlas passed briefly in front of a faint background quasar, the object distorted the radio waves in a way natural comets never do. Instead of a simple smooth refraction pattern, the signal broke into 3 sharp plateaus, exactly matching the 3 internal layers seen in the VLT imagery. 3 layers, 3 seams, 3 plateaus. 1 object. The next question was obvious. Were these layers drifting apart? The answer came from the ALMA observatory. Its millimeter wavelength array captured a full-field interferometric map of dust velocity vectors. What it showed sent a quiet chill through the science team. Each layer rotated at a different angular velocity. Not random, not chaotic, not disintegrating. Layer 1, inner, 0.06 dig IHR. Layer 2, middle, 0.004 dig R. Layer 3, outer, 0.03 dig IHR. All rotating in the same direction. All proportional, all stable. This was impossible for a single rigid body, but it was equally impossible for a fragmented one, unless the object's interior wasn't a solid nucleus but a set of loosely bonded shells, each shifting under finely distributed torque, like nested layers adjusting around a common center. Rhodes exhaled slowly. "That's not a fracture pattern," she said. "That's a mechanism." Nobody wanted that word spoken aloud, but it fit the data too well. Something internal was redistributing stress evenly, keeping the layers aligned but separate. To salvage the natural interpretation, Ishida attempted a physical explanation. Maybe the nucleus contains multiple density strata, each with different thermal responses. A safe idea, a conservative one. But the problem was the synchronization. Natural density layers don't rotate in stable ratios. They don't maintain long-term alignment. They don't respond to the sun with smooth, coherent motion. Then came the event that shut down the debate entirely. At 1852 UTC, the VLT captured a momentary dip in brightness in the outer layer, a soft dimming lasting 11 seconds. At the exact same moment, the middle and inner layers brightened equally, as if the illumination had transferred inward. Dust doesn't transfer illumination. Ice doesn't transfer illumination. Energy doesn't flow between fragments like water passing between glasses. But the glow shifted, cleanly, efficiently, almost deliberately. The team ran it through every known natural mechanism, phase angle changes, dust particle resonance, rotational shadowing, but none worked. The timing was too sharp, the transition too even. Finally, NASA added a new term to the internal anomaly log: coherent layer coupling, not an explanation, a placeholder. Because there was still one more problem, the object's increasingly precise outbound path. Since the beginning of the anomalies, 3I Atlas had executed 4 measurable course corrections, tiny microbursts, each under 1 momentum S2, spaced at intervals that were irregular but not random. Now, the predicted orbit deviated by 0.006 AU from its pre-anomaly model, still small, still subtle, but indisputable. Atlas wasn't just drifting, it wasn't just reacting, it was following something, an invisible trajectory guided by physics no one fully understood. Yet, by November 17, 2025, NASA believed it had catalogued every anomaly 3I Atlas could reasonably produce. They were wrong. At 09:22 UTC, the Deep Space Network's Madrid station, DSS 65, recorded a brief repeating distortion in its carrier baseline, an oscillation lasting 2.9 seconds, repeating every 41 minutes, too faint to trigger alarms, but too structured to dismiss as noise. It wasn't a transmission. No modulation, no encoded pattern, nothing intentional. But it was synchronous, predictable, mathematically clean. Engineers first suspected a calibration error. So they checked the Goldstone and Canberra arrays. Both showed identical fluctuations, offset only by signal travel time. 3 independent antennas, 3 identical distortions. Something near 3I Atlas was interacting with the radio waves passing through its coma. But how? NASA assembled an emergency, cross-disciplinary panel. RF engineers, heliophysicists, comet specialists, and 3 mathematicians from JPL's Autonomous Systems division. Their job wasn't to interpret the anomaly, only to determine if it was real. It was. The distortion followed a strict waveform, a rising cosine envelope, sharp cutoff, brief plateau, then decay, resembling the interference signature of a rotating frame. But nothing inside a comet rotates fast enough, evenly enough, or consistently enough to shape radio noise into a repeating pattern, unless the layered structure discovered earlier, those slowly rotating shells, were somehow modulating the density of the coma itself, imprinting a kind of shadow on passing radio waves. A natural phenomenon? Maybe. But the waveform was too clean. Dr. Helena Rhodes stared at the spectrogram. "This isn't a message," she said. "It's a consequence." "Of what?" someone asked. She didn't answer. To investigate, NASA turned to ESA's Gaia DR4 data stream, which provided ultra-precise astrometric tracking. Gaia observed subtle, rhythmic micro-oscillations in the object's apparent centroid, microscopic shakes on the order of plus 0.7 milliseconds, too small to reveal with ground-based telescopes, but perfectly matching the 41-minute cycle detected by DSN. That meant one thing. The object wasn't just altering the way radio waves passed through it, it was physically oscillating, not spinning, not wobbling, oscillating. A vertical nod, then a horizontal one, repeating like a slow heartbeat. But what could cause a body nearly 700 meters wide to pulse in space? Hypothesis 1. Tidal flexing. Dismissed immediately. Tidal forces from the Sun at 1.5 AU were negligible. Hypothesis 2. Asymmetric outgassing. No jets detected, no thermal signatures, no mass loss. Impossible. Hypothesis 3. Internal mass redistribution. The most conservative idea. If the nucleus was layered, perhaps volatile migration created periodic pressure shifts inside the shell structure. But that raised another question. Why were the oscillations perfectly timed? Nature is rhythmic, but not clockwork. Then came the breakthrough. Quiet, technical, unsettling. A postdoctoral researcher from MIT, embedded at NASA for a rotation, overlaid the 41-minute oscillation with the earlier 23-minute internal precession discovered through JWST data. The ratio was exact, mathematically perfect. 41 minutes, 123 minutes, x 1.7826, a value suspiciously close to the golden ratio squared, 1.7817. Not exact, but close enough that mathematicians in the room exchanged glances. Natural phenomena don't produce near irrational ratios across 2 independent mechanisms without some underlying regulatory system. But no one dared use the word system. It suggested more than any scientist was willing to consider. Meanwhile, the VLT captured something new. A dip, a blink, a momentary disappearance of the middle shell layer, vanishing for 0.3 seconds before fading back in, as though the density had momentarily shifted out of phase with the other layers. Rhodes replayed the sequence at 1/100 speed. "Phase slip," she said, "like resonant oscillators falling out of sync. But comets don't house resonant oscillators. They don't synchronize. They don't desynchronize. And they certainly don't create harmonic interference patterns detectable from Earth." The room fell into a heavy silence. No conspiracies, no speculation. Just the pressure of data that refused to fit into familiar categories. The object was stable, predictable, oscillating, precessing, brightening, adjusting trajectory, each anomaly small, each explainable in isolation. But together they formed a picture no one could interpret. Yet, by November 20th, 2025, the anomalies surrounding 3I Atlas had finally crossed a threshold. Not because they grew stranger, though they did. Not because they multiplied, though they had. But because, for the first time, they suggested a pattern that extended beyond the object itself. The discovery began with an innocuous task. A data intern at NASA's Jet Propulsion Laboratory plotted the last 10 micro-adjustments in 3I Atlas's trajectory into a single 3D visualization. The expectation was simple. Show a line of subtle deflections along the outbound arc. But the plot didn't form a line, it formed nodes, 10 tiny points, each correction less than 1 mila-moment s2, each almost imperceptible. But when mapped in sequence, the nodes traced a shape, a flattened looping curve, resembling a distorted Lissajous figure. Completely natural. Possibly, but highly unusual. When the intern overlaid the oscillation periods discovered earlier, 23 minutes for precession and 41 minutes for centroid motion, something unsettling emerged. The nodes aligned with integer multiples of both cycles. Rhythmic motion inside the object, rhythmic motion of the object itself, rhythmic adjustments in outbound trajectory. 3 independent systems, each acting at different scales, were syncing. Patterns like that don't appear out of nowhere. At 11:14 UTC, the intern showed the visualization to Dr. Rhodes. She stared without speaking, then called a full briefing. Within an hour, the imagery was projected onto the main screen at NASA Goddard. It looked like a diagram, a chart, a path. But no one dared say that aloud. Instead, the team retreated into scientific caution. Is this a natural resonance chain? Could internal stresses be coupling to the spin state? Is this a cometary equivalent of nutation drift? Each scholar offered a possibility, a hypothesis, a lifeline. But each hypothesis collapsed under scrutiny. Natural resonance. Resonances require continuous energy input. Atlas was losing energy. Internal stress cycling. Stress cycles decay. Atlas's cycles were sharpening. Nutation drift. Nutation produces wobble. Atlas produced correction. The object wasn't drifting away from internal instability, it was drifting toward something. The next data set arrived from the Solar Terrestrial Relations Observatory, Stereo A. Its heliospheric imager captured 3I Atlas silhouetted against a dense star field. With the increased background brightness, analysts could see a faint, extended plume trailing the object for nearly 80,000 kilometers. But the plume wasn't diffuse. It contained striations, thin lines of alternating density at near regular intervals. The spacing matched the 41-minute oscillation period. Dr. Ishida tightened the visualization. What could imprint periodic structures in a dust plume? Pressure waves? No. Magnetic braiding? No. Solar wind harmonics? No. The striations were too evenly distributed, too stable. They resembled breadcrumbs, a record of the object's periodic behavior etched into its own trail. And when the plume striations were plotted in 3D, something extraordinary emerged. They curved. They bent, not according to random dust dispersal, but according to the same looping path traced by the 10 earlier course adjustments. The plume itself was copying the internal rhythm, as though the object's oscillations were not just internal, but environmental, shaping everything around it. Then came the final piece, the one that forced the room into absolute, breathless silence. A mathematician from the Harvard-Smithsonian Center overlaid the Lissajous-like path of the adjustments with the projected future trajectory of 3I Atlas. They intersected, not randomly, not broadly, precisely, at a single point in space. At 2:31 AU, 14 days into the future, along a region with no major bodies, no gravitational anomalies, and no known debris fields, the object's anomalies, its pulses, its oscillations, its layer rotations, its micro-adjustments were converging toward that point. A rendezvous? A stress release event? A natural structural collapse? No one knew. But the implications were undeniable. 3I Atlas was not just changing, it was going somewhere, and that destination, empty, unremarkable, silent, was suddenly the most interesting place in the solar system. On December 4, 2025, 3I Atlas reached the point scientists had been watching for 14 tense days, a location with no gravitational wells, no dust clouds, no charged particle gradients, nothing. At 2:31 AU from the Sun, the most mysterious interstellar object ever observed approached its predicted convergence coordinate, slowly, silently, shedding the faint periodic striations that had puzzled every heliophysicist watching the live telemetry. NASA, ESA, and JAXA had coordinated a global observation window. Nearly 47 instruments, from JWST to ALMA to the Rubin Observatory, pivoted to watch a patch of sky no larger than a thumbnail held at arm's length. Everyone expected something: a burst, a structural failure, a fragmentation cascade. Something. Instead, 3I Atlas did what no one predicted. It stopped accelerating. No more micro-adjustments, no more oscillation-induced drift, no changes in precession. All internal motions, 23-minute, 41-minute, and their harmonic echoes, slowed over 6 hours and then stabilized into a single, unified 29-minute rhythm. This had never happened before. The object's layered structure, once chaotic in its complexity, now rotated as one. The radio distortion smoothed, the dust plume straightened. The brightness spike at 890 nm faded into a stable curve. 3I Atlas wasn't reacting, it wasn't struggling, it wasn't collapsing, it was settling. Dr. Helena Rhodes leaned forward as ALMA's interferometric model finalized. "Internal motion has reached equilibrium," she whispered, "a multi-shell resonance in perfect phase." Perfect wasn't an exaggeration. For the first time since discovery, the object behaved like a coherent whole: mass, density, and rotation, all synchronized as though every layer had found a common balance point. Natural, unusual, extraordinary? Yes, to all three. Then came the final observation. Quiet, almost anticlimactic. At 0803 UTC, JWST detected a faint thermal emission wave traveling inward through the shells, like a ripple collapsing gently toward the core. A gravitational event? No. A mechanical stress release? Possibly. A thermal relaxation? Maybe. Whatever it was, it marked the end of the object's active phase. For the first time in months, 3I Atlas behaved like a normal interstellar comet. The layered rotation settled. The oscillations ceased. The brightness plateaued. The dust trail thinned. The trajectory resumed a simple hyperbolic escape. It came to the convergence point. It stabilized. And then it simply continued on. No explosion, no signal, no spectacular transformation. It reached equilibrium and drifted quietly into the dark. 1,000 scientists stared at dashboards expecting more. But space is indifferent to expectations. Nature often performs its strangest acts without theatrics, without explanation, without a headline. Dr. Ishida summed it up best, speaking softly in the dim control room. Whatever happened inside that object, it finished happening. The mystery wasn't solved, but it was complete. As 3I Atlas faded beyond the reach of most instruments, scientists were left with a profound truth. Not every phenomenon offers closure. Not every anomaly resolves into a neat equation. Sometimes the universe presents a puzzle and then carries it beyond the horizon before we can finish reading it. But data remains, the records remain, the shell structure, the oscillations, the striations, the resonance, all preserved, waiting to be understood by future missions, future telescopes, future generations. 3I Atlas didn't break physics. It expanded it, and somewhere, far beyond Mars's orbit, the object drifts toward interstellar space again. Quiet, stable, unchanged on the outside, but forever marked by whatever took place deep within its layered core. A traveler that arrived with secrets and left with them.